Happy Sunday afternoon. I thought I would work a few homework problems for you, so when you're working them later this evening, you'll have something to go on. I'm going to do number 55 first, which is the summation from n equals 1 to infinity of negative 1 to the n plus 1 over n, and that converges to ln of 2. The instructions want you to show using your calculator how to approximate the sum with an error of less than 1/10,000th using as few terms as possible. So the first thing I always do with a series is write out some terms, and so it looks like when we put n equals 1 in, we have positive 1, and then we'll just alternate minus a half plus a third minus ... plus, and then let's talk about getting to 1 over 10,000. That's pretty easy to see even without a calculator how to get there, because the next to the last term will be 1 over 9,999, and so we'll have that. Not sure if it's positive or negative, but to be honest with you, it really doesn't matter. So because this term right here is less than or equal to the error that we're asked to find, then this sum should be within 1/10,000th. And so here's where we pick up the calculator. I put in ln of 2 over here, getting 0.693147, and then using a sigma and a finite sum, so 9,999, we can see that we are within, it looks like 500 thousandths of the requested error. So that one is kind of easy to do. Let's talk about why we can just go to the next term like this. It's because this is a convergent alternating series. So we really don't have to do much work. We just have to figure out getting this inequality satisfied and then going one term in. So that's 55, and that's what you can do when it's alternating. 56 works the same way because it is alternating as well. 57 is when we have to incorporate Lagrange, and I'll be honest with you, that's just harder to do. There's just no other way around it. So let's start off and write terms just like we did before, and this one is a little bit more difficult because we don't have 1 in the numerator. So getting that denominator to be 10,000 isn't going to be as easy to do. So let's start off. We're starting at n equals 0, so our first term is 1. Notice that it doesn't alternate, so we can't use the alternating series error. So then our next term is 2 to the first over 2 factorial, and then plus 2 to the second over 3 factorial, and then plus 8 over, where are we, 4 factorial, and so on and so on and so on. And this would be lovely if this was alternating. I would just keep writing terms until I got 8 over 24 to actually, or the 2 to the n over n factorial to be less than or equal to 10,000. So let's talk about the maximum here. If we were to create this series with a chart, and we don't have to, we would have, let's see, 0, 1, 2, ... n plus 1. So I'm just kind of writing this out. Thank goodness this is e to the x, so e to the x, and then they're all e to the x. And what we do when we're creating this series centered at 0 is we actually evaluate this at 0. So you've got e to the 0, which is 1, and so all of these are 1. That maximum value that over the interval from the center to what we're evaluating this at, and honestly, that is 2. Because you can see that E itself is n equals 0 to infinity of x to the n over n factorial. So you have to ask yourself, is the n plus first derivative, which is, thank goodness, just e to the x, which is bigger, e to the 0 or e squared? And that's a pretty easy thing to answer. E squared is bigger than 1. And so versus with alternating series, you're just putting the 1 in front. We have to put e squared in front to get our error. So we're looking for, where does e squared times x, which is 2, minus 0, which is the center, raised to the n plus 1 over n plus 1 factorial, where is that less than or equal to 1 over 10,000? And to be real honest with you, on Friday afternoon, there was a bunch of us in the room, and we just kept plugging numbers in until we got it to work, which seems kind of, guess and check, but they're giving you a calculator, so that's the biggest thing we have to go on. All right? So when we put this in, we found that that value was n equals 11. And so when we put 11 in, we had e squared times 2 to the 11th over 11 factorial, and we found that that was less than or equal to 1 over 10,000. And actually, I mean 12. Because once we got this to work, then we were able to come up and go one term that preceded that. And you can see from our answers, that works. If you need me to re-explain that in English tomorrow, I'll be more than happy to, but that's your Lagrange error at its hardest, in my opinion, and its most difficult. Let's go on and take a look at 59, which is kind of a weird little problem. I think it's cool, though, that they want us to do it with a series. If you ask me to do this question, I would put 0 in for x, get 0 over 0, and go, oh, let's lope it. So the limit as x goes to 0 of positive sine x over 1 is equal to 0. It's done. Perfect. But they're having us do it with a series, which is kind of cool. So let's start off with cosine. So cosine is 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So that's cosine. And then they want us to manipulate that. If we write out a few terms, which I think is a good idea, your first term is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus plus so on and so on and so on. Then if we write negative cosine of x, that just changes all of those signs. So negative 1 plus x squared over 2 minus x to the 4th over 24 plus minus dot, dot, dot. And then adding 1 to both sides. So again, here's my, that's my goal here. And so I've got negative cosine. When I add 1 to both sides, it knocks out that term. So now when I take all of this and divide both sides by x, then 1 minus the cosine of x over x, just looking at a few terms here, will give me x over 2 minus x cubed over 24 plus dot, dot, dot. And if I take the limit as x goes to 0, then won't all of our terms go to 0? And we knew that was the answer, and so that's pretty cool. 63. 63 is how to handle error with an integral. So the first thing we're going to do is write our power series for e to the x, which is x to the n over n factorial, and then writing it for e to the negative x cubed we have 0 to infinity, negative x cubed to the n over n factorial. Let's write out some terms so we actually have something to take the antiderivative of. When you put in 0, you get 1, and then let's see, minus, we put in n equals 1, we get x cubed, and then we get plus x to the 6th over 2 factorial, and then minus x to the 9th over 3 factorial plus dot, 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 dot. Okay? If I integrate those terms, then the integral of e to the negative x cubed is equal to x minus 1/4 x to the 4th plus 1/12, nope, 1/14 x to the 7th minus 1, 4 times 6, 24th, x to the, what am I doing here? This is supposed to be 9. Sorry, there's my 9, and then this is going to be 60, x to the 10th. And if I need an error of less than 10,000, I've got a long way to go. But when I handle this with factorials, it shouldn't be as bad as it looks. So what I'm going to do right here is just continue to add some terms. So this is going to be x to the 12th divided by 4 factorial, which is 24. And then when I get to here, I'm going to have 1 over 24 times 13, which I'm going to go to my calculator. 24 times 13, I'm really waiting to get to 10,000, is 312, so not there yet. So then I'm going to add another term up here, x to the 15th over 5 factorial, which will be 120. When I integrate that term, I have 1 over 6 times 120, and where that 5 came from is beyond me. Let's go 15 and then 16. Hello, email, go away. Thank you. 16 times 120. And I don't know about you, but I've got a pretty good idea that 120 times 16 is going to take us over, nope, 1920, not there yet. One more term, plus x to the 18th over 6 factorial, which is 720. Let's see if I can actually integrate that right. It will be 1 over 19 times 720. I forgot my x's here. X to the 13th, x to the 16th, x to the 19th. Okay, one more time. 19 times 720. 13,680. Ding, 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 ding. That's going to be big enough. So when I evaluate this from 0 to 1, knocking out this term because it's a convergent alternating series, then my sum is actually from 0 to 1, 1 minus a 4th plus a 14th minus a 60th plus 1 over 312 and then minus 1 over 1,920, and that's an approximation of the integral from 0 to 1 of e to the negative x cubed. And we're not going to do anything with that but stop. Just to confirm, I just plugged all this in the calculator because I know that you wanted to make sure that I didn't steer you wrong. This integral is 0.807511, and the sum of these 1, 2, 3, 4, 5, 6 terms is 0.807446. So bingo, we are within a 10,000th. See ya tomorrow.